My name is Adri bin Abdurrahim. I am currently a final year student in UiTM Shah Alam, studying mechanical engineering currently, completing my final year project entitled Mathematical Model for Cutting Force in Ultrasonic-Assisted Milling of Soda Lime Glass. Soda lime glass has a high demand in market, representing the brittle materials to be machined by ultrasonic-assisted milling, considering two different material removal mechanisms, which are ductile model and brittle model. The modeling of cutting forces is an essential need that relates to the aspects of UAM for glass materials. Mathematical model is defined as the activity of modeling a real-world problem translated into mathematics by forming a model to be used later, providing information about the original real problem. UAM is the innovated conventional milling machine by means of ultrasonic assistance has been already introduced in the past. An overview of specialized ultrasonic components is shown in the picture where inductive input coil is mounted at the spindle nose for non-contact transmission of electric energy to the tool holder's receiving coil fixed at the rotary actuator. Concerning the actuator, the required electric energy is transmitted by a wire-free inductive system enabling full compatibility to automatic tool changes. The main component is the HSK interface with a fixed inductive receiver system in which ultrasonic frequency is transferred from spindle to the HSK holder via induction, and the piezoceramic elements acts as the ultrasonic vibration generator. This is the Gantt chart for my project planning. Due to the pandemic of COVID-19, some changes had been done to the planning as should. Moving forward with the research objective, firstly is to study the material removal mechanism of the brittle material through related literature review. Secondly is to analyze the trajectory motion of ultrasonic machining by programming the equations of trajectory motion of all three axes into MATLAB software. Finally is to predict actual cutting force of material removal without actual experiments after dealing with the mathematical models development also by MATLAB software. Scope of study is firstly going through the related literature review, and next dealing and understanding the mathematical model development, and finally program into MATLAB software. As mentioned earlier, due to the desirable properties of soda lime glass, the material has a high demand in market and need to be machined depending on their purposes. However, the typical properties of brittle and strong of the material made them difficult to cut. Therefore, researchers had been working on the modeling of predicting cutting force for higher productivity and reducing costs. As you can see in the illustration, UAM combines the milling kinematics of rotation in the x-axis with grinding material removal mechanism along with the ultrasonic resistance applied to the cutting tool vibrated vertically along its z-axis. So what are the main parameters involved in the cutting and material processing? Considering number of grains on both face and side, there are three main parameters studied that are feed rate, cutting depth, and spindle speed. Considering two material removal mechanism, ductile mechanism produces a plastic flow of material in the form of severely sheared machining chip. As you can see, the brown area referred to the plastic deformation zone through scratching or indentation of diamond grains. Ductile regime machining follows from the fact that the material will deform plastically if the scale of deformation is small enough to allow a plastic material removal process. While in the brittle mechanism, the MRM is accomplished through the propagation and intersection of cracks. Both mechanisms are proposed in this study, whereby the ductile MRM is removed by the grain indentation into the workpiece surface, while brittle MRM, the abrasive grain indentation initiate cracks that refer to the median cracks just below the contact area. As the contact force is further increased, the indentation progresses towards the work material surface such that the side cracks, referred to the lateral cracks, begin to appear and propagate until reaching the free surface, thus causing peeling off the work material. These are the flow of the mathematical model development that I'll be explaining briefly in 4 main steps. What I need to highlight here is the abrasive diamond grain particles are assumed to be spherical in shape, and obvious Hessian contact theory applied in ductile model, while viscous hardness theory applied in brittle model. Also that not all diamond grains participate in the cutting process, in which only 45% of all abrasive grains are active grains. Step 1 is to understand the relationship between single grain force and the grain indentation depth. This is where the ductile plastic deformation of Hudson indentation theory is applied to ductile model. The indentation depth equation is from Timoshenko and Godier, 1970, is simplified in terms of contact force, while the indentation depth equation for brittle is from B. Lon and R. Wilshaw. Step 2 is to understand the relationship between UAM cutting force and single grain force by means the impulse theorem is applied to find the relation between axial cutting force and impact force. By equaling both impulse, the ductile and brittle model cutting force is obtained by the multiplication of contact force, number of grains phase, effective cutting time, and vibration frequency. So these are the number of grains phase and side equations, where you can see that the equation of number of grains side includes cutting depth inputs that must be taken into consideration during simulation, and also both equation will be multiplied by 0.5, assuming the active abrasive grains. The modeling equation of effective cutting time is done based on the sign graph by assumptions made. Final equation for ductile model, while further simplified our final equation for brittle model. Step 3 is to estimate actual volume of material removed by 1 grain's indentation, U, and calculate the material removed volume, W, from relationship between input variables and MRR. As for ductile model, the indentation volume U of diamond grains penetrating into the workpiece is the intersection between intended spherical diamond grain, and the workpiece will be a part of ellipsoid. So the indentation volume is calculated by the integration as shown, while equation of material remove volume W that relates with input variables of feed rate and cutting depth is obtained from equation of MRR by simplify in terms of W by equaling U and W, and simplify in terms of indentation depth. Indentation depth equation for ductile model is obtained as shown. For brittle model, according to the sharp indentation theory as shown in the figure in the slide, the equation of lateral cracks and height of cracks is from Marshall 1982 and Lon 1980, where KIC is the fracture toughness of workpiece and HV as workpiece hardness, and K2 is the dimensionless constant number. The indentation volume U for brittle due to the brittle fracture is simplified 2 times the volume of tetrahedron ABCD as shown, obtaining U equation, also equaling U and W, and simplify in terms of indentation depth. The indentation depth equation for brittle model is obtained. And these are the equation used to analyze motion trajectory for all 3 axes, and by differentiating ST, we'll obtain the velocity of the diamond particle Vt. By integrating the velocity of diamond grain, effective cutting length is obtained whereby input variables of spindle speed present that had been substituted into actual volume of material removed by 1 grain's indentation, U equation, for ductile and brittle. Final step is obtaining the UAM model cutting force, where you can see is the multiplication of contact force, number of grain phase, effective cutting time, and vibration frequency. Move to the final section of the presentation is the results. This equation is programmed into MATLAB to analyze the trajectory motion of UAM. So the first one is analyzing the motion by excluding the feed rate in the y-axis, where you can see the coding of y where feed rate is absent. Also to highlight that the average tool diameter is defined large of 0.3 meter. So you can see that the formation of static vertical cylindrical shape referred to the milling kinematics and wavy of the cylindrical is the ultrasonic vibration assistance. Next is the coding by including feed rate, also large average tool diameter. When feed rate is included in the y-axis, the material processing mechanism starts along the y-axis. Next is the coding including feed rate but small average tool diameter of 0.003 meter. When the average is defined small, the outcome differs because the motion trajectory is too small for the software to show. Even so, it is still rotating and vibrating while feeding in the y direction. Results from models developed. These are the fixed variables also programmed into MATLAB for cutting force prediction. And these are the equation for ductile model to obtain predicted ductile cutting force. There are three results obtained for ductile model, which are spindle speed versus FD, feed rate versus FD, and cutting depth versus FD. Constant input variables are also showed there for all three graphs. The figures showed that the axial cutting force decreases when rotational spindle speed increases and increases as feed rate and cutting depth increases. In figure B, when feed rate increases, the relative cutting out length of each abrasive grain becomes longer and the machining loading increases, causing higher cutting force. For figure C, by increasing the cutting depth, increases the volume of removed material, which in turn increases the corresponding cutting forces needed to remove the material. While for figure A, however, when spindle speed increases, the chip thickness decreases, leading to lower cutting forces. Moreover, it is found that the ductile mode produces higher axial force compared to the brittle mode, where the specific cutting energy increases as the indentation depth increases, leading to increase the axial force. And these are the brittle model equations, whereby different equations of indentation depth and cutting force are programmed in MATLAB. In case of brittle mode, the cracks initiate, propagate, and intersect, thus cause deterioration of the material strength, which in turn decreases the axial force compared to the case of the ductile model. Moreover, the study is found to be interesting by observing the cutting behavior as the axial force varies strongly with a change in spindle speed, feed rate, and cutting depth. Three different values of feed rate are programmed as well in MATLAB, plotted in graph for both models, shown in figure A and C, whereby the axial forces jump in higher feed rate, but the axial forces plunge when spindle speed increases as shown in figure B. It is found that the mathematical model developed for both models do not have limitation in order to predict the axial forces, as the trend graph plotted similar, although faster value of feed rate of 300 mm per minute and faster value of spindle speed of 18,000 RPM are programmed into MATLAB. Due to the fact that the cutting force predicted is not similar from adopted literature, error analysis had been done by extracting data of predicted cutting force from adopted literature through a website known Webplot Digitizer to be compared with my own based on the same input variables. The extraction of data is obtained by interpolation. However, they could possibly be inaccurate. For spindle speed versus ductile cutting force, the highest error calculated is 12% at the lowest RPM of 2000, and the error calculated decreases as spindle speed is set faster, showing ductile mode occurs at higher spindle speed, while lowest error calculated at slowest feed rate of 20 mm per minute, showing ductile model prevails at low feed rate. And for cutting depth, showing lowest error calculated at smallest cutting depth of 20 micrometer, and the error increases as cutting depth is set bigger, means that ductile model prevails at low cutting depth. Country-wise for brittle model, The error analysis showed that brittle model prevails at lowest spindle speed and highest feed rate, and at highest cutting depth. The predicted cutting forces obtained are validated by comparing experimental data that also had been extracted through web plot digitizer at constant input value of 100 micrometer of cutting depth and plotted in graph. For the ductile model, at 20 millimeter per minute in figure A, the experimental results start to getting nearer to the ductile model results, where the percentage error calculated dropped from 45.81% to 15.86%. That indicates the material is removed under ductile mechanism until reaching the feed rate of about lower than 30 millimeter per minute, after which it shifts to brittle material removal mode of fracture cracks. The feed rate value in which the model shift from ductile model to brittle model is called model transition feed rate, and corresponding axial cutting force is called model transition cutting force. The values of penetration depth obtained from the indentation depth equation for both models showed that the lower penetration depth referred to ductile material removal mechanism, and by increasing the penetration depth, the mechanism of material removal referred to brittle. It has been found that at low feed rate, the experimental results are closer with ductile model with lower percentage error, while further increase in feed rate with corresponding cutting depth shows lower percentage error in brittle model. The ductile model prevails at small values of feed rate associated by low material remove volume through obvious peeling off marks of material. However, brittle model is dominant at large values of feed rate, producing high material remove volume because of cracks and fracture of removing material. And also validation of results at constant value of feed rate at 80 millimeter per minute from adopted literature. At cutting depth of 20 micrometer in figure A, the experimental results start to move closer to the ductile model results, where the percentage error calculated dropped from 20.99% to 2.36%. That indicates the material is removed under ductile mechanism until reaching the cutting depth of about 32 micrometer, after which it shifts to brittle material removal mode of fracture cracks. The cutting depth value in which the model shift from ductile model to brittle model is called model transition cutting depth, and corresponding axial cutting force is called model transition cutting force. It is noticed that at low cutting depth, the experimental results are closer with ductile model with low percentage error calculated, while further increase in cutting depth with corresponding feed rate shows lower percentage error in brittle model. Brittle model is dominant at large values of cutting depth, producing high material remove volume because of cracks are initiated and propagated and fractures occurred of removing material, showing 0.01% of error calculated at 100 micrometer cutting depth, while ductile model prevails at small values of cutting depth associated by low material remove volume under the assumption of material removed by plugging or grains indentation is proper. And that is the mathematical model for cutting force in UAM of soda lime glass. What I talked about was, in this project, it shows that brittle materials capable to experience two different material removal mechanism under ultrasonic machining methods, which are ductile mechanism and brittle mechanism. Also, the trajectory motion of UAM capable to make transition of material removal mechanism through indentation of diamond grain, in which the models predicted trends that are generally comparable and in line with the experimental data from adapted literature. And the models also helps to allow greater understanding of the effects of these two mechanisms on process inputs and cutting forces. Further study or work could be done using different brittle materials such as ceramics or even composites, considering these two mechanisms of ductile mode and brittle mode, or also could be done to analyze the tool wear or even temperature predicted relation with cutting force for both models. That's all from me. Thank you. For Q&A session, do contact me through my email or my phone number via phone call or WhatsApp.